Assalamu alaikum and good day everyone. Today I'm going to present my final year project, which is the effect of nanofluids on the heat transfer performance in a mini-channel flow. So to begin, why nanofluid is used in the first place? Day by day, the electronic devices are getting miniature. As a result, it leads to the development of integrated circuits of ultra large scale magnitude, which is a new generation of high performance dense module. However, on the consequence of increased power density and extreme heat flux, long-term reliability and efficiency is hampered, as conventional liquid fail to provide desired heat removal from heat flux, generating electronic devices and heat exchangers. My research is on the use of nanofluid to combat such problem. Nanofluid is a thermal engineered fluid capable of giving remarkable heat transfer improvements than the conventional fluid. So the literature behind the claim is showed here. First one, conventionally water is used as the working fluid to transfer heat through mini-channel. But water is not a good and efficient working fluid. The reason behind this is if water is used, there will be higher mass flux, but pressure loss is higher than the mass flux while flowing through the mini-channel, is said by Koji Inoki. Another one is by Awais, which is with the replacement of traditional fluids with nanofluids and flat heat transfer surfaces with corrugated surfaces. Numerous researchers have achieved remarkable thermal and pressure drop efficiency. There are two reasons for this. First, the introduction of corrugated surfaces increases the turbulent strength and the mixing of fluid flow, providing a higher rate of heat transfer. Secondly, due to the higher thermal conductivity, the addition of nanoparticles to the base fluid further improves the heat transfer efficiency. Now, why mini-channel is used? So the literature behind it is Tuckerman and Pierce first used the micro and mini channels in heat sinks that vary from traditional channels in terms of hydraulic channel diameters. They postulated that the heat transfer coefficient can be increased by decreasing the channel hydraulic diameter. So in their work, several researchers have shown remarkable performance of nanofluids, which are enlisted here. This is the problem statement of my project. Number one, which is current mini-channel flow having low thermal conductivity and not so efficient in absorbing heat from the walls of mini-channel. Number two, normally water have low thermal conductivity, not so efficient in heat conduction from the walls. Here is the objective, which is to improve the thermal conductivity of the heat transfer fluid, and the second one is to demonstrate the effectiveness of nanofluid in heat transfer in mini-channel. This is the scope of my project, where nanofluid which will be used is alumina water nanofluid, where the concentration of alumina is 0.5% to 3% in different nanofluids. The temperature of the fluid at inlet will be around 27 degrees Celsius. Laminar flow will be used with Reynolds number ranging from 100 to 2000. Heat flux will be at 100 kilonewton per meter square. The channel which will be used is a straight channel. Material of the channel is copper. Now, what is the significance of this project? The significance of this project is to provide a better thermal solution for high heat flux generation machines and equipment, which in turn helps to sustain the lifespan of the machines. Nowadays, like, the computational power of the chips are getting higher and higher due to the demand of this current world. So at the same time, it emits a lot of heat, which requires a very nice and efficient cooling system. Cooling system is very important for electrical components and machines to run in optimum temperature and perfect performance. Here in chapter 2, the methodology is described. The focus of this research is to demonstrate the effect of nanofluid on the heat transfer performance in a mini-channel flow. A summary of the studies on the employment of nanofluids, which is a alumina water-based nanofluid in various shapes, is present in the table below. So the first researcher is Ahmadi et al. The nanofluid which he used is alumina and water-based nanofluid. Configuration type is mini-channel with cylinder, no fin, wavy fin and flat fin. The result is nanofluid concentration increment. With the increment of nanofluid concentration, thermal conductivity improves. Heat transfer enhancement by 200%. Decrease in the particle size increases the heat transfer coefficient. But the second group of researchers, Louis, Chai, Wang and Zhao, the nanofluid they used is the same, alumina and water-based nanofluid. The configuration here is in curved duct, and the result is alumina nanoparticle in a curved duct increase the convective heat transfer. Nanoplatelets show the highest convective heat transfer and pressure drop among all other shapes. Here the results of three groups of scientists are shown, where in overall the result which came, which is the increase in nanoparticle concentration and the increase in the Reynolds number overall like increase the heat transfer performance of the fluid. So to perform the heat transfer analysis, the methods which are used are briefly explained here. As in other science and engineering areas, heat transfer analysis utilizes experiments, numerical simulations, and theoretical methods as instruments to promote research and development. The experimental approach is more accurate, but the simulation is more preferred than experimental measurements or theoretical analysis due to factors such as speed, cost, repeatability, and safety, coupled with recent technical development and widespread access to computers. So I'll explain here the method which is used for this research. The three-dimensional forced convection flow and heat transport were modeled using Ansys Fluent 2021 R1. It is a commercial CFD solver. In the simulation, the control volume method from the finite volume method was utilized. The convective and diffusive components were discretized using a second-order upwind interpolation technique, while the velocity and pressure fields were linked using Spalding and Patinker's semi-implicit method for pressure-linked equation, which is also known as simple algorithm. When the normalized residual values for all variables fell below 10 to the power -6, the convergence conditions were established. Now the Ansys report of geometry and mesh is going to be shown here. This is the model and shape of the mini channel which is used in this project. This is the inlet. The red portion here shows the fluid part. This is the outlet which is shown here with a red mark. This is the heated wall which is just above the applied heat flux. And here the symmetry is shown. And the insulated walls are shown here. Here a report on model geometry and parts is shown, which is generated from Ansys software. This is the report on the model materials, the report on the coordinate systems. Now the mesh report is shown here. Here we see the quality of the mesh. So according to orthogonal quality mesh metric, the average is 1, which is considered quite good mesh quality. Here some other mesh results are shown. These are the mesh control results. And the results for the named sections. That's all for the Ansys report of geometry and mesh. Now we go to the grid test. 5 different hexahedral shaped mapped mesh sizes were generated by edge sizing along with x-axis, y-axis and z-axis. All those were coded M1, M2, M3 and M4, M5. The relative error of the desired parameters was computed using the following equation here. Now the result of the grid test. J signifies any parameter. The selected parameter was Nusselt number. J1 and J2 signify the parameter values acquired from finest grids and other grids respectively. Between the second grid M3 and the fourth grid M4, the relative error in the Nusselt number is negligible, and the solutions on the grids with 320,000 elements and 480,000 elements are determined to be less than 0.5%. The similar trend was exhibited for friction factor between M3 and M4, while the error is nearly 3% for M2 with M4. To reduce computational time and memory, all simulations in this work were run on a grid M3, which is with the elements 320,000. The governing equations which were used in this project are briefly shown here. The Navier-Stokes equation are used to model the laminar flow to resolve the results of the fluid. As a consequence, the steady-state fluid control equations are as follows. Mass conservation equation is here, momentum conservation equation is also shown here, and also for the energy conservation. Now, to find the properties of the nanofluid, the following equations were used. For the base fluid, these equations are used, and to calculate the density and specific heat of the nanofluid, the following equations were used. Nanofluid viscosity is attained by using the model below. And to test the thermal conductivity of the nanofluid, these equations were used. Here, the thermophysical properties of water and alumina nanoparticle by Chengel and Afshin is shown here. Here are the boundary conditions which were used, and different concentrations were taken into account, which will have an inlet temperature at 27 degrees centigrade or 300 Kelvin, uniform and continuous heat flux as much as 100 kilonewton per meter square is applied on the channel walls as the thermal state. Additionally, the relative pressure is set to 0 at the channel outlets. At inlet T equals to T naught, which is 27 degrees centigrade or 300 Kelvin, V equals to V naught. At outlet, gauge pressure is 0, and at the valve, V equals to 0. Now, on chapter 3, the results and discussions are done. It is found out the heat transfer coefficient is higher for 0.5% concentration of alumina based nanofluid compared to other nanofluids. On the other hand, pressure drop is highest for 0% concentrated deionized water, and pumping power is the highest at 0.5% alumina water nanofluid. The rise in pressure drop might be attributed to an increase in velocity as concentration and viscosity rise, as well as the expansion and contraction of the follow path, which disrupts the boundary layer and promotes heat transfer. The overall thermal convection of heat transfer fluid increases with the increase in Reynolds number. Here are the results on heat transfer coefficient. Here, according to the results shown in the table, it is seen that the nanofluid with concentration 0.5% of alumina performs better than the other nanofluids and also the water. Now here, according to the figure, it is seen that the pressure drop is the highest in water while compared to the rest of the nanofluids. However, in this figure we can see that the nanofluid with concentration 0.5% has higher pumping power compared to the rest. The thermal resistance of all the nanofluids and including the water reduces with the increase in the Reynolds number, which we can see from this figure. To conclude, all nanofluids showed better heat transfer performance with the increase in Reynolds number. However, nanofluid with concentration 0.5% alumina water showed better heat transfer capability compared to the pure deionized water and nanofluids with other concentrations, although showed higher requirement of pumping power compared to the rest of the nanofluids. This brings me to the end of my presentation. Thank you so much for your attention and interest.